Step 1. Applying textual patterns to privacy policies. We use the Atlas Cloud MongoDB document database to store all the data in JSON-like documents. These documents include details related to privacy policies, devices, events, users, nudges, and personal identifiable information. In reality, privacy policy documents are unstructured. Thereby, we manually read and categorized them into 4 elements as user action data and purpose. Here, we have concatenated multiple policy statements under associated events of IoT devices. When logging device and sensor information, the service provider processes a list of end-user data. These personal data are used for analyzing trends and usage. Step 2. Creating users and user groups. We have created 2 user groups as employees and owner to provide individual or shared access and control for each organizational setups in smart buildings. Users have been created and assigned based on their authority. Step 3. Create a list of personal identifiable information types and assign their risk levels. We have created a PII bank in our document database to list all the sensitive and non-sensitive user information that possibly be used and transferred with a request payload. Each type is linked to a reasonable risk level based on its sensitivity. Step 4. Creating IoT device-specific events and assign applicable policies. There are vendor-defined device-specific events for each IoT device. And each event has to adhere to a set of privacy policy statements initiated by the vendor. Step 5. Creating a list of IoT devices in the smart building. To represent a smart building, we incorporated multiple devices, including smart lights, door locks, TVs, and temperature sensors. Step 6. Mapping users with devices to manage access and control. Some smart devices are restricted for personal use, and some are permitted for shared use. Based on the room and area where the user is located, we provide multi-device, multi-user support, maintaining an end-to-end relationship. Step 7. Maintaining logs of privacy infringements. We have developed APIs to perform the privacy policy check by capturing every event's request payload. All the applicable policies are tested, and the result is logged as true or false to indicate any policy infringements. Finally, the output is used for generating nudges to enhance user awareness. Step 8. Recording nudge details. Nudges are generated for all the privacy infringements that occurred while triggering device-specific events. These nudges are logged to track the same nudge's recurrence for the same PII type that has been sent out and ignored by the user. Step 9. API development and deployment on Amazon Web Services. We have currently written 3 APIs to trigger IoT devices events, generate nudges, and track the user's privacy permission changes. We link the MongoDB models to query records based on the payload data. The Trigger Event API acts as a publisher to a specific topic on the Mosquito MQTT broker, which runs on our Amazon cloud server. Therefore, the mobile application, IoT automation tool and voice assistant act as consumers for the API. Simultaneously, according to the device token, IoT device ID and event ID, we query an array of applicable privacy policies for the policy check to generate nudges. Finally, we visualize the nudge content in 9 different ways based on the previous response for the same policy infringement. We chose Amazon Web Services as our infrastructure and, using the CLI credentials, deployed the written APIs on the AWS instance. It created an API gateway and Lambda functions in the AWS cloud services. Then we configured the IoT core to provide access to the MQTT message broker. We can now make REST API calls to our Cloud API endpoints, publish messages to the MQTT server, and configure MQTT with Node-RED. Step 10. Designing Node-RED data flows. We included 7 smart light interfaces, 4 smart door lock interfaces, 2 smart TV interfaces, and 5 smart temperature sensor interfaces for a sample smart office space. We used special JavaScript function nodes, switch nodes, change function nodes, HTTP network nodes, link and subflow nodes to make reusable flows. While the API acts as a publisher, the Node-RED server acts as a subscriber to our Cloud MQTT broker from the same topic and credentials to trigger an action. Thereby, we can now control all the device interfaces remotely. This data flow design can be recognized as a reusable artifact and are key contributions to this study. Step 11, Dashboard Overview for Remote Control. IoT dashboard represents a digitalization of the physical world in a single interface. We have been inspired by the Humanize Labs floor map and replicated its open plan working space, meeting rooms, and supervisor and postdoc rooms with multiple smart devices. Also, these devices are installed in a certain way that only privileged users can control them. For instance, the devices installed in Grundy's office cannot be controlled by a postdoc or a student. Step 12, Mobile App Development and Nudge Visualization. For the convenience to visualize and to respond to nudges in changing privacy settings, we have developed a mobile application. It communicates with the deployed APIs in triggering events and visualizing generated nudges. A nudge highlights what privacy settings are ethical and righteous to be practiced in influencing user behaviors. The responsiveness rate to a nudge varies with diverse user personalities, as some end users might need extremely demanding nudges to support privacy decisions. Thereby, we inherited the concepts of threat coping appraisal, loss gain aversion and herd behavior. A nudge consists of 3 elements: a summary of the unauthorized actions, redirecting instructions to the privacy settings, and an opt-out option.